Well, hello. Tonight we're going to finish the other kinematic equations. And tonight we'll again be working on our vertical adjustments to the kinematic equations. We're going to talk about gravity as we go along, and we're going to work on solving some practical problems. Our first one here is, we've had it already. The slight adjustment we've made now is instead of having an A in here, we've inserted a G. We've talked about this quite a bit now in class. Hopefully this is becoming easier for you, but this is the acceleration because something would be falling. All right, the acceleration due to something falling. Real quickly here, if something, to find something's final velocity, a lot of times if VI is 0, meaning we're dropping it off a cliff, or if it's falling from a ledge, or something like that, it will simplify down into just VF equals G times T, which is the same thing. It's just we don't write the 0 in there. So I wanted to make a little acknowledgement of that. Our average velocity equation here, it is missing a bar above it, so we'll put that bar up there. But this equation doesn't change at all. The bottom one changes only by putting y's in instead of x's, and g in for a. So there's the only thing it's changed. I want to talk about this equation right here real quickly, the top one, our average velocity, because we haven't talked about that hardly at all. Today sounds like a good time for that. I'm going to take a pause here and draw some stuff so we can save some time. Well, what I've drawn here is I've tried to draw like a mountain or a hill of some sort. And let's imagine that we have this object, and I've drawn these circles on here. And there's these objects, and they're going to roll down this hill. Well, what's nice about this is at the top we can say that its initial speed was 0 meters per second, and at the bottom we can say that its final speed was 20 meters per second. Well, what was its average speed over the course of this way of rolling down the hill? Well, our average equation over here says that we can simply put 20 in, we can put 0 in, and 20 plus 0 is 20, divided by 2 is 10. So its average speed was 10 meters per second. Well, why are we able to just do that? Well, the reason is because, as we've been trying to say in class, we have this constant acceleration. Whatever was pulling it at this point is the same thing that's pulling it down the hill at this point. It has the same acceleration. If for some reason Earth became 5 times larger and gravity changed halfway down this hill, then the acceleration, the thing that's accelerating it, would change, and we wouldn't be able to use the equation for the entire trip. But because we know the Earth isn't going to become all of a sudden 5 times larger, we can say that the acceleration it's experiencing at the top of the hill is the same as the acceleration at the bottom of the hill, and that allows us to use our average velocity. I believe one of your problems in your assignment deals with a cheetah, and it tells us that the cheetah can accelerate. Well, it has the same acceleration over that 2.8 seconds. So we can use this average velocity equation, to solve that one. Okay, for this first problem, I've run ahead and made a list already to try to save us a little time here in our notes. And it's asking us, what is the maximum height reached by the rocket? Well, what's happened is the engine has stopped. So this acceleration, we've got to kind of decode, is useless to us because it's no longer accelerating at that rate. So that's no longer of importance to us because it tells us the engine has stopped. So what I'm going to do is I've got to pick one of my equations that gives me a distance because I want to find out what height it went. I've only got 2 of those. So then my choice becomes which one to use. Well, one requires time and one doesn't require time. So I'm going to use the one that doesn't require time because they don't give me any time in this problem. And what I'm going to go ahead here then and say is I'm just going to leave this as y right now, and you'll see y in a short bit. Okay, what I've done is went ahead and worked this out after I read the equation there, and what we get is I put VF in a 0. Because when the rocket finally stops, when it gets to its maximum height, the rocket is going to no longer be moving up. Because if it's still moving up, it's not at its maximum height yet. So I'm going to put 0 in for its final velocity. Its initial velocity at that 150 meter mark when the engine stopped is it was going 50 meters per second. We have 2 times g, which is 2 times negative 9.8, which gives us the negative 19.6, and then y. So at this point, what I did is I solved for y, and it goes an additional 127.6 meters. That's on top of the already achieved 150 meters. So the total height would be 277.6 meters is how far this rocket, that is the maximum height achieved by this rocket. Okay, what I've done here is I've went through and decoded this problem, made myself a list of information. In this case, I'm not going to use g, because the acceleration that's acting on this rocket is not gravity. The acceleration that's acting on this rocket is due to the engine. And it tells us in the story problem that the engine accelerates at 3 meters per second squared. What they want us to find out is what is the final velocity, or what is the velocity of the rocket when the engine stops. I've added the word final in there to kind of help you decode it, to realize that's what we're looking for. So once again, I need to use a problem that uses displacement, acceleration, and velocities. So that only leaves me with one choice. Okay, what I've done is I've worked it out for us, and I went ahead and included the initial velocity of 40 meters per second, squared it. I put the acceleration in of 3, so 2 times 3, and the displacement's 150. 2 times 3 is 6, times 150 gives us 900. 40 squared is 1600, which equals 2500. When I square root that, I get a final velocity of 50 meters per second. That's how fast it was going at when the engine had turned off. Okay, I went ahead now and included another problem here for us to work out. Actually, this is going to be one of the ones that you work out. It says a rock is dropped straight down from a window that is 40 meters upward. What is the maximum speed reached by the rock? Well, let's go ahead and make ourselves a list. They want to know that final speed, so I don't know that one. The initial speed, because it's being dropped, we can say is 0. Gravity is what's acting on it. That's negative 9.8 meters per second. Of course, I wouldn't have to use the negative because it is asking for just speed, but we'll pretend that that was really velocity. And they don't give me a time, but they do give you a displacement and say that it's 40 meters, how far it's being dropped. I'm going to go ahead and pause it and give you a chance to work that out. I'm going to give you a hint. They don't give you any time in this problem, so you're going to have to use the the equation that doesn't use any time. I went ahead now and used this problem and included a list over here to the left. As you look at the list, again, there's one component I'm not seeing, and that is time. You're going to have to use a problem or an equation that does not include time. That's the biggest hint I'm going to give you. We can talk about those tomorrow if you want. The last thing I'm going to give to you then is this problem. It says a ball falls for 3 seconds after it's dropped from a roller coaster. How fast is it going after 3 seconds? Well, did they give us time? They do. It's 3 seconds. Do I know initial velocity? Well, if it's dropped, you can assume it to be 0. They're wanting you to find that final velocity. I will give you this hint. What's pulling on it? Gravity. So, work on these 3 problems. I know some of you are saying, probably one of you at least, saying, Mr. Kimmel, there's only 2 spots. Adapt. You'll figure it out. You're all smart kids. I'll see you on the flip side.